Hello everyone! This lecture is devoted to the basic concept of discrete mathematics, which are necessary for the course of geometric modeling. The topic of this lecture is fundamental notion of mathematics, and this notion is sets. The picture on this slide shows the stained glass at the Cambridge University, commemorating John Venn, one of the mathematicians who made great input to the set theory in the form of the Venn diagrams. All materials for this unit, such as lecture notes and seminar handouts, are available at the following link. Today we cover the following topics. We start from notions for sets, then Venn-Euler diagrams, and finish the topic with basic set operations and their properties. Unlike many other branches of mathematics, where the formulation of ideas and concepts occurs gradually over time and is developed by many mathematicians before it is formalized into a single theory, the formulation of set theory is almost the single-handed creation of one mathematician, namely Georg Cantor. He was born in Russia to a Danish father and a Russian mother and spent most of his life in Germany. Between the years 1879 and 1884, Cantor published a six-part treatise on set theory, where he introduced some of the fundamental notions of this theory, and followed this by a publication of a two-part treatise between the years 1895 and 1897. Where he clarified and systematized what he had introduced in his first cycle of publications. Since its introduction, set theory has proved of great importance to the modern formulation of many topics of continuous and discrete mathematics. In current mathematical practice, such topics as numbers, relations, intervals, functions, and transformations are defined in terms of sets. In our study, we will frequently use sets to explain a number of other mathematical concepts. Thus, it is important to gain a good understanding of sets and set theory. Let's give a notion of a set. A set is a fundamental mathematical notion that is formally undefined and can be only intuitively understood as a type of structure representing an unordered collection of zero or more distinct objects called elements. Georg Cantor gave the following definition. A set is a gathering together into a whole definite, distinct object of our perception and of our thought, which are called elements of the set. Although this appears to be a simple idea, sets are one of the most fundamental concepts in modern mathematics. Set theory deals with operations between, relations among, and statements about sets. All of mathematics can be defined in terms of some form of set theory, and sets are also extensively used in computer software systems. Naive definitions turned out to be inadequate for formal mathematics. Therefore, the notion of a set is taken as an undefined primitive in axiomatic set theory. There are two most basic properties of a set. The first one, a set has elements. The second one is equivalence. Two sets are equal if and only if they have the same elements. So let's discuss about a set membership. Sets are denoted with the capital letters. Elements of a set are denoted with lowercase letters. If an object X is a member of a set A, then we denote this relationship by the following statement, which reads X belongs to A, or X is a member of A, or X is in A. If an object X is not a member of a set A, then we denote this relationship by the following statement, which reads X does not belong to A, or X is not a member of A, or X is not in A. This symbol, which means belongs to, was introduced by the Italian mathematician Giuseppe Pino in 1888, derived from the first letter of this Greek word, meaning is. We may define a particular set in two distinct ways. The first one is listing all the members. The second one is using membership rule or semantic description. This is example of a list of set members. The set A, whose elements are 2, 3, 6, 8. This is a tabular form of the set definition. These are examples of another so-called set builder form. Here these symbols, vertical stroke and colon, are read as where. A more general set builder form can be written in the following way, and is called a set membership rule. This statement denotes the set S of all entities X for which the predicate or condition P of X holds true. Such membership rule works like a black box, evaluating elements according to a predefined condition. One more variant of the set builder form is the following expression, which denotes the set S of all elements X that belong to the set A and for which the predicate P of X holds true. Next example describes the set of odd integers. Here, predicate P of X can be written as X is odd. Let's take a look at the basic properties of sets. And the first notion is the empty set. A set that contains no elements is called a null set or an empty set, and is denoted by the shown symbol. For example, if A is the set of all people in the world who are older than 200 years, then A is the empty set. In this case, we can write down the following expression. Next example, if the set B will be constructed with the following set builder form, it will be empty set 2. The empty set is the unique set that can be defined by the following equivalent set builder forms. The next notions are finite and infinite sets. A set is finite if it consists of a specific number of different elements. In other words, if the process of counting its elements can terminate. Otherwise, the set is infinite. Here there are three examples and different types of set definitions. If D is the set of days of the week, then D is a finite set. Another example, if O is the set of all odd numbers, then O is an infinite set. And if M is set of all mountains of this planet, then M is finite set, even though it may be very difficult to count all the mountains. Let's discuss cardinality and finiteness of sets. The cardinality of set S is a measure of how many different elements this set has. For example, cardinality of the empty set is 0. Let's consider other three examples. Cardinality of set with the numbers 5, 6, 7 is 3. Cardinality of set which contains only two letters A and B is 2. Cardinality of set of sets is 2, as it includes two elements. If cardinality of the set S is a natural number, then we say S is finite. Otherwise, we say that S is infinite. The next notion is power set. The power set P of a set S is the set of all subsets of S. For example, the power set P of the set with two letters A and B is 4. It includes empty set, singletons A and B, and the set with letters A and B itself. Sometimes P of a set S is written as 2 to power S, because cardinality of power set P of a set S is equal to 2 to the power of cardinality of S. It turns out that for all sets S, cardinality of power set P of a set S is larger than cardinality of S. For example, cardinality of power set P of the set n of natural number is larger than cardinality of n itself. Remember for now, there are different sizes of infinite sets. The next topic is Venn-Euler diagrams. Venn diagrams are illustrations used in the set theory. They show mathematical or logical relationships between sets. A diagram of a set is based on a two-dimensional closed curve, which together with its internal area represents elements of a set. With Venn diagrams you can see that one set is a subset of another, just by seeing that you can draw an enclosure around its members that fits completely inside an enclosure drawn around the larger set's members. British philosopher and mathematician John Venn introduced the Venn diagram in 1881. A stained glass window on the first slide of this lecture is installed on the Cambridge University, where Venn studied and spent most of his life. This window commemorates him and represents a Venn diagram. The example of Venn-Euler diagram is shown on this slide. The universal set U represents all animals. C represents the set of all camels. B represents the set of all birds. A represents the set of all albatrosses. The whole Venn diagram represents the relationship of these sets. This Venn-Euler diagram illustrates two sets A and B, which have a pair of identical members E3 and E4. In the diagram, the intersection of these sets is shown. Next topic is basic set operations. We will discuss such operations as union, intersection, and difference with symmetric difference operation. Also disjoint set definition, inclusion-exclusion principle, and set complements. Let's start from the union operation. The union of sets A and B is the set of elements that belong to set A or to set B or to both sets. We denote the union of sets A and B by the following statement, which reads A union B. Next expression is a definition of the union operation using set builder form. Example: if the set A contains symbols A, B, C, D, and the set B contains C, D, F, then the union of these two sets will contain A, B, C, D, F. The union operation has following properties. First of all, it is commutative, and both sets are subsets of their union. These Venn diagrams illustrate the union operation. The left diagram shows sets A and B as two ellipses as boundaries of the initial sets. The union of sets A and B is the set of elements that belong to set A or to set B, or to both sets. Therefore, the result of the union is shown in yellow color in the right diagram, where each point belongs at least to one of the initial sets. Here are two examples for you. The first example of union is relatively simple, because two initial sets do not have common elements. The second example illustrated by the Venn diagram shows the union of sets having common elements. This slide illustrates the union operation using line segments. Next operation is intersection. The intersection of sets A and B is the set of elements that are common to both sets. We denote the intersection of sets A and B by the following statement, which reads A intersection B. Next expression is a definition of the intersection operation using set builder form. The intersection operation is shown in the example and is illustrated in Venn diagram. This operation has following properties. It is commutative as union operation, and intersection of two sets is subset of both sets. Here are intersection examples. The first example shows that intersection of two disjoint sets without common elements is an empty set. The second example shows the situation when the intersection is not empty. This slide illustrates the intersection operation with line segments. This example illustrates the situation when the two sets intersect in one point, and this point is 0. We can say these two sets are joined. Let's consider the disjoint sets a definition. The sets A and B are called disjoint if their intersection is empty. Simple example, the set of even integers is disjoint with the set of odd integers. Now let's try to calculate how many elements are in the union of two sets. To answer this question, we use a special method of calculating the cardinality, which is called the inclusion-exclusion principle. For example, how many students are on our class list? If we have two lists, the first one is a list of students in the attendance sheet. The second one is a list of students in the email list. We need to add up the number of students on both lists and subtract the students that are duplicated. So we will see this basic counting principle again when we talk about combinatorics. Next notion is difference operation. The difference of set A and B, in other words subtraction of B from A, is the set of elements that belong to set A and don't belong to set B. We denote the difference of sets A and B by the following statements. Here is an example and illustration this operation in Venn diagram. It should be noted the difference is not commutative. It means subtracting of set B from set A is not equal to subtracting set A from set B. Examples of the difference operation. The first example shows the difference between two finite sets. The second example shows the difference between the set of integer numbers and the set of natural numbers. The result is a set of non-positive integers. Note that 0 is not included in the natural numbers. 0 is not included in set n in the number theory, but it is included for convenience in some applications. The following two slides show an illustration of the difference operation on the number line. Here is one more example of the difference operation on the number line. Next notion is set complements. When the context clearly defines the universal set U, we say that for any subset A of U, the complement of A, written as A with overline or A prime, and it is complement of A with respect to U, meaning that A prime is the difference between U and A. For example, if U is a set of natural numbers, then the complement of set A is A prime. The Venn diagram shows the relationship between A prime, and U. The following slide shows the illustration of the set complement example on the number line. So, if the set A contains only one element and this element is number 1, then the set complement of A will be whole number line without this number 1. The next operation is a symmetric difference. The symmetric difference of sets A and B is the set of elements that belong to one of the sets A or B and do not belong to both sets. For example, if the set A contains symbols A, B, C, D, and the set B contains symbols C, D, F, then the symmetric difference of sets A and B will be following symbols A, B, and E, F. The symmetric difference of sets A and B is subtraction the intersection of these sets from the union of these sets. This slide shows the illustration of the symmetric difference example on the number line. This figure simply illustrates the basic set operations we have just discussed. The next topic in our lecture is membership tables and constructive solid geometry. The set membership tables are similar to truth tables for propositional logic. It shows all values of the statement depending on the different values of the constituent sets. This table is built using following rules. Table columns are used for different set expressions. Table rows are used for all combinations of the membership in constituent sets. If statement contains n constituent sets, then the set membership table will contain 2 power n rows. Number 1 is used for indicating membership in the derived set, 0 for non-membership. The set membership tables is used for proving equivalence of set expressions with identical columns. Let's consider an example of building a membership table. There are four basic kinds of elements, otherwise basic regions of Venn diagram. The ones that are in neither A nor B, the ones that are in B but not A, and so on. Everything analogous to truth tables, but based on the different regions of a Venn diagram. The proof shows that the two formulas cover the same basic regions of the diagram. That is the same kinds of objects. Here is one more extended example of building a membership table. Let's prove the equivalence of these two statements and build a membership table for that. We will fill out the table consistently for all sub-expressions for each statement. The first sub-expression will be A union B. The next expression will be subtraction C from the union A and B. The next sub-expressions will be subtraction of C from A and subtraction of C from B. On this slide, let's calculate the expression on the right side. Now we can see that set expressions are equivalent. Next notion is constructive solid geometry, abbreviated as CSG. It is one of the main representations of solids based on a set of three-dimensional solid primitives and regularized set theoretic operations. Traditional primitives of a CSG system are block, cylinder, cone, sphere, and torus. Standard operations include union, intersection, difference, plus translation and rotation. A complex solid is represented with a binary tree, usually called CSG tree. Don't be surprised, please. These trees are growing with the root up and leaves down. A typical binary structure includes the root, purple color, nodes, pink-orange, and yellow leaves. In the case of the CSG tree, the root represents the resulting complex object. The nodes contain operations and the leaves contain primitives. If a node represents a linear operation, translation or rotation, such a node has only one child subtree, as example operation 4. All nodes with set operations have two children, operation 1, 2, and 3. We will consider the CSG representation in more detail in the following lessons. The next topic is called N-sets. It means that we will consider the representation of sets with numbers greater than 2. Venn diagram for n sets must contain all 2 power n hypothetically possible zones that correspond to all combinations of inclusion or exclusion in each of the component sets. 2 power n zones correspond to the number of rows in the set membership table. For example, if n is 2, then Venn diagram has 4 zones. If n is 3, then Venn diagram has 8 zones. If n is 4, then Venn diagram has 16 zones, and so on. This slide illustrates a Venn diagram with 8 zones. This slide illustrates Venn diagrams with 16 and 32 zones. In the shown example of a Venn diagram, different sets are shown as colored ellipses. The most general superset here is shown in yellow and includes all integers numbers from -1 to 9. It has four subsets such as positive integers less than 10, shown by the green ellipse, prime numbers less than 10, orange color, and odd and even integers, red and blue color. In 1989, Anthony Edwards developed an elegant method for drawing Venn diagrams that produced highly symmetric drawings. Examples of such diagrams can be seen on this slide. Now let's look at generalized union and intersection operations. Since union and intersection are commutative and associative, we can extend them from operating on ordered pairs of sets A and B to operating on sequences of sets A1, A2, AN, and so on, or even on unordered sets of sets. This is just like using sum operation when adding up large or variable numbers of numbers. Let's consider the generalized union operation. For union two sets, we use the binary union operator. N-ary operator is used for union of several sets of more than two. Grouping and order are irrelevant in union operation. There is special symbol for this operation, and this symbol is used for infinite sets of sets. The same principle is used for the generalized intersection operation, but of course we employ other symbols. The next topic is Cartesian product. Before we continue with the Cartesian product, let's consider definition of tuples. The ordered n-tuple is the ordered collection with the element ai being the ith element, for i1, 2, 3, and so on. Two tuples are considered equal if their lengths are equal and the elements standing in their respective places are equal too. A two-tuple is called an ordered pair. The Cartesian product of two sets A and B is defined to be the set of all pairs A and B, where A belongs to set A and B belongs to set B. It's called the Cartesian product since it originated in decade formulation of analytic geometry. In the Cartesian view, points in the plane are specified by their vertical and horizontal coordinates, with points on a line being specified by just one coordinate. In the example, you can see how all possible pairs form the Cartesian product of two sets. This operation is also called the product set, set direct product, or cross product. Let us mention one more term important in digital computing, especially in databases. The set R is called a relation between A and B if it is a subset of their Cartesian product. Here is example of Cartesian product of two sets. Subset of Cartesian product R is called a relation R with the sets A and B. As shown in the example, this subset is a relation over these two sets. Note that for finite sets A and B, cardinality of the Cartesian product is equal to the cardinality of A multiplied by the cardinality of B. Another property is that Cartesian product is not commutative. The notation of the Cartesian product extends naturally to the product of multiplied sets. The next representation scheme is the sweep representation, or simply sweeping. A set of all points visited by an object A moving along a trajectory B, see on the top image, is a new solid, called a sweep. In translation sweeping or extrusion, two-dimensional area moves along a line orthogonal to the plane of the area. In this small animation, the non-regular area is moving along the axis x and sweeps a three-dimensional solid. This slide is just a reminder of basic terms and notations related to the set theory. The next topic is Algebra of Sets. Let's consider the general rules in Algebra of Sets. Here is U is a universal set and A, B, C are subsets of U. The identity, complement, and idempotent rules are shown on this slide. Associative, distributive, and De Morgan rules constitute properties of set operations, similar to those of standard arithmetic operations, such as summation and multiplication. Let's illustrate the associative rules. Following two slides illustrate the associative rules with three sets A, B, and C. The verification of the associative law for the union of sets using Venn diagrams is shown on this slide. The verification of associative law for the intersection of sets using Venn diagrams is shown on this slide. Let's consider the distributive rules. Following two slides illustrate the distributive rules with three sets A, B, and C. The verification of the distributive law for the union of sets using Venn diagrams is shown on this slide. The verification of the distributive law for the intersection of sets using Venn diagrams is shown on this slide. Now let's look at the De Morgan rules in more detail. The following next slides show the verification of the De Morgan rules using Venn diagrams. This is De Morgan's law of union. Complement of the union of sets A and B is equal to the intersection of complement A and complement B. This is De Morgan's law of intersection. The complement of the intersection of sets A and B is equal to the union of complement A and complement B. The next rule, subtraction of the union B and C from the set A is intersection of subtractions B from A and C from A. And subtraction of the intersection B and C from the set A is union of subtractions B from A and C from A. The summary table about set identities is shown on this slide. Thank you for your attention.